Okay, so following on from the previous presentations, I'd like to present a little bit about the European Ground Motion Service. I assume that since you've attended for the last 2 days, you have an idea of what it is, but I will go over about the service itself as well. So what is the European Ground Motion Service? It's a new service from the Land Monitoring Service, providing continental scale measurements of ground motion all over the Copernicus participating states. And it's free of charge and it's accessible to everybody. So what we have done, and this is a consortium of several INSAR producers in Europe, we have processed 150,000 Sentinel-1 images. And from this, we've produced data for about 10 billion locations across Europe, covering all 30 countries. From this, we've generated about 15,000 what we call basic products. I'll go into the different products in a minute. Another 15,000 calibrated products and about 1,500 ortho products. And altogether, uncompressed volume of the data is about 20 terabytes. But if you were to download it all from us, it would be about 6 terabytes. Each one of these measurement locations has a lot of data behind it, about 300 individual data points or data values. So altogether, we're talking about many trillion data values. And then the question is, what is ground motion? Well, we've used ground motion as a very general term. So basically, we're using the satellite to capture any kind of motion on the ground. And when we say ground, we mean either the natural terrain, so for example, volcanoes, landslides, and so on, or, for example, infrastructure that's on the ground, roads, railroad, bridges, buildings, and so on. And the 3 products that I mentioned earlier, the basic, calibrated, and ortho, the basic product is what many people who have used INSAR before are used to. It's a calculation of the ground motion. It's a relative movement between an arbitrary reference point in the data set and the point in question, and it's all along the line of sight. What we have done in EGMS is we have taken advantage of the synergy between GNSS for large-scale motion detection and measuring and INSAR for very fine-scale measurements. So we have created something called the calibrated product, where we have taken each of these 10 billion INSAR line-of-sight motions and combine this with a velocity model that we've generated based on the GNSS network in Europe. And we've put all the INSAR data into a geographic or geodetic reference frame. The final product, which is the first product you see when you go into EGMS, we call ortho. And this, for the ortho product, we've taken all the available data at any given 100-meter grid cell in the data set, and we've combined them to calculate or estimate the vertical motion and the east-west motion. And you'll see a bit more of this as I go through the demonstration. So this is an example of the basic product. As you said, this is what you're used to seeing in most INSAR data sets. This is near Tromsø. We see a lot of motion on mountainsides. And this is the calibrated product for the same area. And you see suddenly that we have motion, the general motion is upwards here. And this is due to post-glacial uplift in Scandinavia. And then this is the ortho product showing vertical and east-west components. So the vertical component on the top right is very similar to what you saw for the line of sight, where in general the land is moving upwards, except for some landslide areas. And in the east-west component, you see motion along slopes very often. So where do you find this data? The best place to see and work with the data is in the Explorer that we have developed. This is a web-based, fully 3D map server, which shows all these 10 billion measurement locations and has the ability that you can add your own data to interact with as well, or to either interact with our data with your data in the background. You can look at the motion velocities for each point and also look at the history of the deformation for them. And also we have download functions recently added. And for this, I'm going to move on to a live demonstration of the service. So this is what you see when you first come into the EGMS portal. We see you have a map browser looking very much like a Google Earth. We can pan and zoom as standard map functions using the mouse, the scroll bar. If you're using this on a touchscreen device, you can pinch and zoom and pan using your fingers. And the other interesting or nice part about this is that this map is fully three-dimensional. So if we zoom in onto a mountainous area in Norway, for example, and if I use the right mouse button, I can turn the map as I would in Google Earth, and I can zoom in on an area. And this is very useful if you're trying to interpret the motion data on a slope, for example. We have a toolbar that's in the browser, in the Explorer here, which has a number of tools to interact with, including a search function. So for example, if I type in Paris, I come up with the various districts in Paris, and I can click and I can zoom straight to Paris. Or some other place in the UK. If you are out in the field, for example, and looking on this in the mobile device, or if you just want to quickly go to your home location, you can click on the compass point. The browser, if you haven't done this before, will ask you if you want to allow it to know your location. If I allow it, this is going to zoom straight to where I'm sitting now in Trondheim. If you click on one of these points, that's red, for example, we pop up a second window here, which shows the motion of that point over time. So along the x-axis, you have the measurement date, and along the y-axis, you have the cumulative displacement. You might notice there are gaps in the data here. This is because I've clicked on a point up here in Norway. When we have areas which have significant snow cover, we cannot do a proper estimation of the motion during the snow-covered months. So we discard those scenes. If we were to do the same exercise somewhere in Europe, in mainland Europe, we will not see that. If you want to compare multiple points, you can hold down the Shift key and click on a nearby point and compare the two motions. In the top left-hand side, you can choose the layers that are available. The default when you come in is this ortho-vertical layer, which is the 100-meter gridded product showing the estimated vertical component. We also have the calibrated product, which has a much higher resolution. If I turn off the ortho product and turn on the calibrated product, you can see that now we are down to the building level of the number density of points. You can see if you click on one of these points that sometimes it's a little bit noisy. However, we also have a tool that you can compute the average of a number of points. And this will give you a better idea of the overall motion and reduce the amount of noise in these time curves. And once again here, if you hold down the Shift key, you can draw another polygon. Whoops, perhaps not. Yeah, you can compare multiple points. When it comes to data layers, we also have a number of background layers available. The default background layer that's turned on is the very high resolution image mosaic from 2012. We also have the 2018 version available. The reason we've chosen to have the default as 2012 is because there are a few gaps in that data set, for example, in the United Kingdom. Another very important function is that we can add your own data to the layer using WMS layers. We do this using this tool here. So for example, if we were to go to look for geological data, we can go to the European Geological Survey's EGDI webpage and find a lot of various WMS layers that are available. So for example, if we're interested in the pan-European faults, we can click on this layer and come to more detail about that available service. And here we have all sorts of information about this service, including its WMS layer URL. So we can copy this URL. We can put it in here. And we can add the layer. And now you'll see that in our legend, we now have, in addition to the previous layers, we now have geology layers from the BGR. And we can navigate down and find, for example, faults. Oops, now I've zoomed out. There we go. So now we can, I might have to turn off the data to see them. But here you can see a European fault map has been added to the background layer. So you can find all sorts of WMS layers that you can add. They won't all work. They have some basic requirements. They have to support HTTPS and various headers and have to have the right map projection. But most of the major sources of WMS layers will allow this. We can also change the color scale on the data sets using the standard legend feature here. So the default is plus or minus 20 millimeters per year. Sorry, we can change this here either using some various features in the drop down, or you can type in your own numbers in the boundary box. And we have various color scales available. If the default red to blue, which is somewhat standard in our field, isn't good for your color blindness, for example, or are there reasons you want a better map, you can choose from various other color bars. For sharing the data, maybe I'll go to a fresh browser window here. If you've zoomed in on an area and you find it very interesting, here, for example, we're in northern Italy, and you see there's a lot of areas with red, which are local landslides motion. We have a button here which allows you to share this view. It will generate a URL, which you can share by email or any other means, that will bring the user directly to this view with these layers turned on and this geometry. Also the same if you want to share, for example, the results for a single point, you can generate a graphics file of these plots to either include in a figure in a report or to send to somebody. In this plot also, you can see the individual data values within this point, and these can be copied and pasted into Excel, for example. If you want to work with this data in your own system in ArcGIS or QGIS or something, we have the possibility to download the data. To do this, you need to log in. So if I open up the archive toolbox here, it tells me I'm not logged in and I must log in first. Clicking on the login link will take you to EU login page. Perhaps not while I'm full screen. Yes, here it goes. Where you can put in your username and password. And we're taken back to the map. So now, by default, we're going to be searching for ortho products. We can zoom in on an area of interest. And using this archive search tool, we can draw a polygon of interest. and find the available data. It comes up here in this legend window. And here you see we have the ortho up products and the ortho east-west products for 4 different tiles. If you move your mouse around, you'll see the tiles highlighted. For each layer, you can download the data or you can zoom in on it just to look in more detail if it's the right location. If you decided that you'd really wanted to download the calibrated data instead, you could turn that on, and the same search polygon would be active. And once again, you have the ability to download individual data sets. You can also click on this link that says download links. It will just give you a text file with all the URLs, which you can then use to programmatically download the data. Each of the links has a token that's generated due to the need to be registered with EU Logon, and this token will continue to be active up to 1 hour after the last downloading is taking place. So if you have a large amount to download, it's no problem to download it, even if it takes several hours. I can show you a few more examples of the type of data that we're looking at. Oops. Here, for example, is Mount Etna in Italy. Now we're looking using the calibrated data. So this is the data that's shown along the line of sight. And we have a descending geometry turned on. If I click on one of these points, I can explain better what this ascending and descending means. The radar satellites are looking down along an angled path towards the ground. And this is illustrated here in this part of the window. So in this case, the satellite is looking down at an angle of 36 degrees in this direction. And if we were to look at the ascending data, we would see that the data is looking in another direction. You can see there are some, this is a temporal unwrapping area due to the very rapid motion in this area. So this shows you the movement direction that you're looking at with these calibrated products. If we were to do the same thing using the ortho data, you can see now that really we're looking at the up-down component always for this ortho up. And if we're looking at the east-west, red is towards the west and blue is towards the east. Sorry. Okay. Another example of types of motions that we see, this is in southern Spain, or rather, and here we see a very large area that's red. And this is due to overuse of groundwater in this area for many decades. And here you see that this whole region is undergoing up to 5 centimeters per year of subsidence due to groundwater extraction. It's a very even pace here. In other cases, we might see a seasonal effect due to increased use of groundwater during certain types of the year. Another example of long-term subsidence. Here, we're back up to Trondheim, where I'm sitting now, and we see the pier area in Trondheim. I'll turn off the data for a minute. In this area here has been built out over the last century using anthropogenic fill out into the fjord. And this fill has been is basically reclaimed land, and this fill has been slowly compacting over the years. And this still today ends up with about 2 to 3 centimeters per year of compaction. Similarly, just over here towards the east, we have a new residential development that's being built out into the fjord using rock mass that was extracted during the construction of a tunnel. And here again, you see very clearly a compaction that's taking place over time. But in this case, it's slowly starting to, or rather, it's starting to even out towards the end. In some cases, we can also capture very sudden motion. See if I'm in the right place here. For example, in this neighborhood in Trondheim, there was construction in this area, and which led to a rapid change of groundwater level. And this drop in the time series, unlike the one in Mount Etna, which is due to inability to estimate the fast motion, this is actually a real deformation that's taking place quite suddenly in 2018, with about a 1 centimeter drop in the ground level. I'll just go back to the Explorer demo. So if you want more information about how to use the browser functions, you can click on the I button in the toolbar, and you'll get a full summary of how to navigate and all the various tools that are in the system. If you click on Help button, you'll get ability to send an email to the help desk, and please feel free to ask any questions at all. We're happy to answer. And if you click on the Info button, you'll come to the European Ground Motion Service page on Copernicus, where you have all the documentation that's available, including algorithm theoretical basis document, which explains how we produce this data, product user manual showing examples of how to use it, end user interface manual, which goes into more detail of all the things I talked to today, and various other quality assurance reports and so on. And that's all I have for today. Thank you.